Kaon and I don't know, a lambda on. Those specific names aren't important. You do need to recognize them as referring to hadrons. And they realized that this combination always seemed to occur exactly like that, even though they didn't see any reason why quarks couldn't form together in a different way. So they figured there's some strangeness going on here. So they said, hey, there must be some other quark, we don't know about it, let's call it a strange quark, because we don't know how to understand it. So they said, okay, we have a strange quark. They figured it behaved exactly like the up quark, but differently. It had the same charge, but a much bigger mass, which would explain the heavier particles they're encountering. And they figured there was some quantity being conserved from beginning to end of the reaction called strangeness. So kind of like here, your lepton number is conserved. So you go from 0 to +1 and -1 with your anti-lepton. Still here, there is a strangeness value. So they figured the pion had a +1 strangeness, proton had 0, and then one of these had to have 0 and the other +1 as well to conserve that. So then they looked back at the model they had. Up until then, they realized they had 4 leptons, the electron and the electron neutrino paired together in one family, and the muon and the muon and the muon neutrino paired together in a family. They saw the up and down paired together in a family. And scientists really, really, really like things to look pretty. They like what they call symmetry, where things that work one way work similarly in a different way. So they were like, hey, if we have all these families, we should have 4 here. We should have another quark that matches up in a family with strange, and we figure it should have a negative charge, kind of like a heavier down quark. So now that they realized that could exist, they started looking for it, and eventually they found it. They found some other quark that behaved just like a down quark, but heavier. They called it a charm quark. And they were thrilled, everyone was celebrating, they were like, hey, this is awesome. And then they found an even heavier electron. They had no idea what to call it. It was incredibly massive. I'm going to try to find the specific weight. But basically, you had this super heavy electron, and they're like, hey, this has to behave the same as all of these other stuff. So they figured that it had to have its own set of neutrino, called the tau neutrino, which it did. And they discovered that much later on you have a really, really heavy neutrino. And reactions with stuff of particles bouncing off each other and changing into different particles by exchanging quarks, they found that there was some number conserved that they called the tau lepton number. So you have these always pairing up with neutrinos to their leptons, and neutrinos will interact with those. And I'll answer your question in just a second. Actually, no. Question?
Shouldn't the charm and the strange split? Because I thought charm would have a +2/3 charge, and strange have -1/3.
You are correct. Thank you. Yeah. So you're right. Strange was related to the down, and up was related to charm. I reversed that. So it looks like that. So up, down, strange, charm, top, bottom. Makes kind of like a zigzag pattern. So looking at this, they had found this heavier, basically heavier electron. And so they're like, hey, we have 3 families here. Let's look for a 3rd family of quarks, because then things will be pretty, and we can make a table, and it'll look nice. So they looked and they looked and they looked and looked and they couldn't find it. And they had the up quark, which had a really, really, really tiny mass. Down quark, which had a slightly larger mass. Strange and charm quarks, which are in the range of 10 to 50 times heavier. And as it turns out, the top and bottom quarks, well, what they ended up calling it, were over 1 million times heavier than all of these. Like, top and bottom quarks weigh more than a lot of atoms. And so they didn't find it because the energy required to create some mass of the mass that they were was enormous, and they weren't smashing things together with enough energy to spontaneously generate those. I like spontaneously generate a top quark and an anti-top quark. And so eventually they did find those. And there was a huge celebration, and they were like, okay, we're done now. And so as of we know now, there are 6 fermions, or quarks, that behave according to how Fermi, the scientist Fermi, described. There are leptons, basically 3 heavy, 1 electron and 2 heavier electrons that have neutrinos with zero electric charge. Electrons, muons, and tauons have -1. And they found that they can smash stuff together using energy to either rearrange how quarks were arranged within hadrons, within those clusters of 3, or they could just have a lot of energy in one area of empty space, and then suddenly a particle and its antiparticle would appear with opposite properties. So think opposite electric charge, same mass, because as far as we know, mass has one direction of charge, positive mass. Like, it doesn't make sense to have negative mass. We haven't found anything that does. But it'll have opposite electric charge, opposite of whatever lepton or quark number it has. Strange charm top and bottom have their own conservation number. So anytime a top quark decays, it gives off, I think, like an anti-top quark or something like that. And they will have basically opposite color charge as well. There we go. And when you have something with opposite color charge, that's called a meson. So you have, here we go. You have a hadron with red, green, and blue all bound together. And it's super fun. From the distance, they look just white. You can't discern that there's any color charge there at all. Here, let's say you have a green top quark. Well, you're going to have an anti-green anti-top quark. And so they figured that because of that, those two together, it looks like there's nothing there. Because you have, remember, the same as with your positive electric negative charge. If you have positive green and negative green, they cancel out. They call that a meson, just a pair of a quark and an anti-quark. So we're going to take a short break